Hello and welcome back to educator.com and welcome back to biochemistry. So in the last lesson we started our discussion of thermodynamics, and today we're going to finish off our discussion of thermodynamics before we move on to another aspect of bioenergetics, which is going to be adenosine triphosphate. Okay, so let's go ahead and continue on where we left off. So in the previous lesson we ended with the following equation. We said that the free energy change for a reaction is related to the equilibrium constant by this equation, minus RT. So delta G equals minus RT ln KEQ. Now this is under standard conditions. So this, let me go ahead and put that there. So this is under standard conditions. And when I say standard conditions at this point, I'm talking about the transformed biological standard, because now we're no longer dealing with chemistry standards, we're dealing with biochemistry standards. So everything pretty much the same, except the pH is now 7 instead of 0. Under standard conditions, excuse me, standard conditions. However, but most, well, not most, all, I'll just write most, but most physiological conditions, but most physiological circumstances do not have standard reactant concentrations, standard concentrations. Well, you know what? I'm not going to write that. Let me just say, let me start again here. So let me erase this. Okay, but under physiological conditions, under physio conditions, things are not standard. Things are not standard. In other words, your concentrations are not all the same, 1 molarity or 1 atmosphere. You have different concentrations of different things. So you might have 3 molar adenosine triphosphate, and you might have 0.1 molar adenosine diphosphate. So when we talk about a standard, again, this is just so we have some point of reference and frame of reference by which to measure something. But again, physiological conditions, concentrations are not going to be 1 molar, and they're certainly not going to be the same for all of the species that are involved. Okay, so the actual free energy change, the actual free energy delta G, is calculated as follows. So we have a way of finding the actual free energy under a given set of physiological circumstances based on what we've calculated under standard conditions, deviation from that. So it's calculated as follows. And this is the important equation that we want you to know. So delta G RXN, reaction, but you know what, I'll just put delta G, equals the delta G standard plus RT ln Q. Now notice, this is RT ln Q, not KEQ, because now we're talking about a situation that is not at equilibrium. The equation up here, this expresses a relationship between the equilibrium constant and the standard free energy change. This says that these are just different ways of looking at the same thing. One is just a constant times the other. What this equation tells us is that under a given set of circumstances, what's my temperature, what are my concentrations, given my base of a standard free energy change, what's the free energy change under that circumstance? In other words, which way will the reaction actually go based on how things really are at that moment? So this is the equation that we want you to know. This is the one that's important. Now Q is exactly the same expression as KEQ, except it has concentrations not at equilibrium, but it has concentrations at any given moment. Now, 3 hours from now, 30 seconds from now, at the particular moment. So Q The expression is still the same as the KEQ. So it is going to be C raised to the C power, D raised to the D power, A raised to the A power, and B raised to the B power, but it's at any given time, not at equilibrium. The KEQ is a measure of the concentrations at equilibrium. It's actually characteristic for that reaction under a given set of circumstances at a given temperature. But here, Q at any given moment. So that's how we calculate the free energy for any given set of circumstances. Okay, now, when delta G ends up being less than 0, this means the reaction is spontaneous. In other words, it will proceed to the right as written. To the right as written. Until it reaches equilibrium. That's what's interesting about this, until it reaches equilibrium. Remember what we said, the free energy change is a measure of the potential to want to reach equilibrium. Once a reaction actually starts, it's like, well, once a reaction actually starts, the delta G, as the reaction moves forward and moves towards equilibrium, the delta G is actually going to rise. So negative 50, negative 40, negative 30, negative 20, negative 10, negative 5, 4, 3, 2, 1, 0. When the system reaches equilibrium, now the system is exactly where it wants to be. It doesn't have a tendency to go this way or that way. In other words, it has no more free energy to release. So that now the delta G is 0. So as a reaction moves forward, delta G changes and moves towards 0. So until it reaches equilibrium. Now at equilibrium, the delta G actually equals 0. This is very, very important. Okay. Now at equilibrium, delta G equals 0. This means all of the free energy available to do work has been used up. That's it, it's done. There's no more once the system reaches equilibrium. Okay. So, this is the take-home lesson. The measure of whether a given reaction under given conditions will move forward, spontaneously as written is delta G, not delta G standard. So under a given set of conditions, it's delta G that we calculate from this equation right here that tells us whether a certain reaction will move forward. The delta G standard is a point of reference. Things deviate from that. Sometimes it'll be more spontaneous than the standard conditions. Sometimes it'll be less spontaneous than the standard conditions. It might switch altogether depending on what the conditions are. That's what's important here. Okay. Now, let's rewrite the equation. Delta G equals delta G standard plus RT ln Q. Well, we said at equilibrium, the free energy is equal to 0. So at equilibrium, that means this left side is equal to 0. That means delta G plus RT ln Q Well, when I move this over, what I end up getting is my original equation that I had from the last lesson, equals minus RT, except now, because we're at equilibrium, instead of Q, we write KEQ. So at equilibrium, you recover the relationship. And again, this relationship is a relationship between standard free energy change and the equilibrium constant. But at any given, for any particular set of circumstances, it's delta G that we're interested in. That's what's going to tell us whether the reaction will move forward or will not move forward, and how much free energy we actually have at our disposal. Okay. Now, delta G is a measure of the maximum theoretical amount of free energy available. The actual amount is much less. So delta G is a measure of the maximum theoretical amount of free energy available. So let's say we have a particular reaction under a given set of conditions, and we calculated that the delta G for this reaction is negative 50 kilojoules per mole. Well, that means that I have 50 kilojoules of, per mole that I can do something with, whether it's build a macromolecule or run some molecular motor or transport some solute across a membrane. Whatever it is that the body needs to do and needs energy for, it has these 50 kilojoules available to it. However, that's a theoretical number. It's not going to use all of those 50 kilojoules. The actual amount that ends up actually being used for useful work is actually a lot less than that, probably somewhere in the neighborhood of about 30 to 40% of that. The rest of it is actually given off as heat. Okay, so the actual amount is always less. Because some, actually most, I should say, free energy is always lost as heat, entropy. I have $50, but in order for me to actually go to the shop where I need to spend $50, I have to give $30 to the person at the door, so that leaves me with $20 to spend. That's what's going on. I have to spend that $30 in order that I can, do a little bit of shopping if I want to do some shopping. That's all that's happening. Okay, let's do an example problem here. Let's go ahead and do this in blue. Oops, let's make sure we get it in blue here. So, example problem number 1. Problem 1. Okay, let's consider again our glucose 1-phosphate reaction to glucose 6-phosphate. And our delta G, standard for that, minus 7.3 kilojoules per mole. It was actually a little bit more than that, so I must have gotten this number from a different, okay, so negative 7.3 kilojoules per mole. Now, if the concentration of G1P equals 0.3 molar, and the concentration of G6P equals, let's say, 1.7 molar, okay, is this reaction spontaneous as written at 25 degrees Celsius? Okay, well, we have 0.3 molar, we have 1.7 molar, so these are not standard conditions, so the concentrations are different, but we have an equation that deals with this. We have the delta G under a given set of conditions equals the delta G under standard conditions plus RT, ln, and Q. Now we just go ahead and put these in. And of course, Q is going to be the products, the G6P concentration over the G1P concentration, which is the reactants. So, and again, we have to account for the units. So we've got, well, the delta G standard is minus 7.3 kilojoules per mole. So let's use minus 7,300 joules per mole plus 8.315 is R. T is 298. And we have the logarithm of Q, which is going to be 1.7 over 0.3. Concentration of G6 phosphate is 1.7. Concentration of G1 phosphate is 0.3. And when we run this calculation, we end up with minus 7,300 plus 4,298 for a total of minus 3,002 joules per mole. Okay, so now the delta G is minus 3,002 joules per mole, which is minus 3.0 kilojoules per mole. Well, it's still spontaneous. It is negative, and it's negative 3 kilojoules per mole. But notice, under standard conditions, it's more than twice as spontaneous. That's negative 7.3 kilojoules per mole. So under these circumstances, I only have, about 3,000 joules of free energy available. And let's say we only end up using about 50% of that. So I'm really going to only end up with about 1,500 joules that's going to actually do useful work. In this particular case, if the conditions were standard, I have 7.3 kilojoules per mole. So I would have a lot more available. I would have about 3.5, 3.6 kilojoules actually available for real useful work. So under these conditions, it's the delta G that's going to tell us how much free energy we actually have available if the reaction is still spontaneous. Obviously, if these numbers change, we can actually change the spontaneity. We can make it so that it actually doesn't want to move forward under standard conditions. Perhaps it wants to move backward depending on what these numbers are. Okay. Now, let's see what we can do. Now, let's leave it as blue. So individual reactions. Individual reactions that have species in common, can be added. And common species can be canceled on either side of the arrows to yield a net equation. Do you remember back in general chemistry when you guys did Hess's law? So you wanted to find the enthalpy of a particular reaction. Well, you knew that if you had the enthalpy of like 2 or 3 or 4 other reactions, but when you added those reactions together and manipulated them in such a way so that when you actually added them straight down and species canceled, if you ended up with your net reaction, what you could do is just add the enthalpies, and that'll give you the enthalpy of the reaction that you want. This is the same thing we're doing here. We could do the same for free energy, the same thing that we do for enthalpy. If there's we can add equations, cancel species, and the final equation that we get is perhaps the equation that we're actually interested in. So that's all that's going on here. Now, the actual free energy of the net equation equals the free energy of the first equation plus the free energy of the second equation. So the free energies are additive. However, the equilibrium constant of the net equation is equal to the equilibrium constant times the second equilibrium constant. So the equilibrium constant of the first equation times the equilibrium constant of the second. So KEQ is multiplicative, the free energy is additive. Very, very important. Let's do an example here. Okay, now the first step of glycolysis, which we'll be getting to very soon, glycolysis, which is the breakdown of glucose, is glucose plus an inorganic phosphate goes, well, I'll just write it as a single arrow, goes to glucose 6-phosphate plus H2O. And the delta G for this is equal to positive 13.8 kilojoules per mole. So this is positive. It's a positive delta G. This reaction, what this tells me is that this reaction does not want to go this way under normal circumstances. In fact, it wants to go the other way under normal circumstances because this is positive. It's spontaneous in the reverse direction. So this reaction is not thermodynamically favorable. Let's write it in red. So this reaction is not thermodynamically favorable. And yet the reaction takes place all the time. It's not dynamically favorable. So how does it proceed? So how does it proceed? Very, very interesting. This is very, very profound, what we're about to do here. Well, let's look at another reaction. Well, let's look at, I'll do this in blue. Let's look at adenosine triphosphate plus water, so the hydrolysis of ATP to ADP plus inorganic phosphate. Well, we've seen this one several times. The delta G for this is negative 30.5 kilojoules per mole. Highly exergonic. Definitely wants to move forward. What I'm going to do is, let me see if I can put this reaction and this reaction together. And let me see what I come up with. Okay, so I have reaction number 1, which is gluc plus Pi goes to G6P plus H2O. And we said that the delta G for this equals, what did we say, 13.8? 13.8. I won't write the units, it's kilojoules per mole. And our second reaction, we have ATP plus H2O goes to ADP plus an inorganic phosphate. And the delta G for this one, we said, was minus 30.5 kilojoules per mole. Well, watch what happens. H2O cancels H2O, Pi cancels Pi. What I'm left with is glucose plus ATP goes to G6P, glucose 6-phosphate, plus ADP. We said that the delta G's are additive, so 13.8 minus 30.5. I end up, and I hope you'll confirm that I've done my arithmetic here. So the delta G of the net reaction is equal to minus 16.7 kilojoules per mole. Okay, look at what we've done. We've taken glucose 6-phosphate. We want to do this reaction. We want to take glucose to glucose 6-phosphate. But under normal circumstances, we can't just put it in the vicinity of some inorganic phosphate and hope to God that it reacts. It's not going to react. 13.8, it's not thermodynamically favorable. However, if I couple it to a highly exergonic reaction like the hydrolysis of ATP, which is highly exergonic, by adding them together, I end up with a reaction that actually goes from glucose to glucose 6-phosphate. It is thermodynamically favorable. Now the reaction has become viable. So what I've done is I've coupled a non-thermodynamically viable reaction with one that is very thermodynamically viable, and in the process, I've actually created a way for the process to happen that is thermodynamically favorable. This is called coupling. Okay, so now we do this in black. Now, the conversion of gluc to G6P becomes viable. The enzyme hexokinase, which catalyzes this particular reaction, that reaction, hexokinase, provided an alternate pathway by coupling. That's the important word here. You'll see it a lot. By coupling an endergonic reaction, reaction number 1, to an exergonic reaction, reaction number 2, through common intermediates. Through common intermediates. We're going to use the energy available here to compensate for the fact that there's not enough energy there. Intermediates. Okay. The energy available in, or from, I should say, the energy available from ATP hydrolysis. Hydrolysis is used to drive an otherwise endergonic reaction. This is a huge theme in biochemistry. This is how the body does it. It couples fundamentally endergonic reactions. You know, again, doing things that the body needs to do takes a hell of a lot of energy. So these reactions don't just happen spontaneously. They need an energy source. Adenosine triphosphate is your energy source. It couples endergonic reactions with the exergonic reaction of ATP to run these reactions forward. That's what's going on. So to derive otherwise endergonic reaction, but by a different pathway. And that's what's important, this idea of a different pathway. Okay. Now, so we have our first reaction, glucose plus phosphate. Okay. Now here's what's important to remember. When we couple this reaction, the reaction that's actually taking place in the enzyme is this reaction right here. Glucose is going to be brought into contact with ATP. A phosphate group is going to be transferred to glucose. It's going to turn into glucose 6-phosphate, and it's going to release the ADP. So when the enzyme opens up again, it's going to release the new product, and it's going to release the ADP. Now, what we say, what you'll often hear biochemists say, what you'll hear your teacher say, what you'll read in books, is that the reaction of glucose to glucose 6-phosphate is driven by the hydrolysis of ATP. However, it's very, very important to remember that ATP isn't actually hydrolyzed. Water doesn't actually come in and break it up to produce a phosphate, and then this free phosphate reacts with this. So reaction number 1 and reaction number 2 don't actually take place. Neither one of these takes place. What takes place is the coupled reaction, this one right here. This is very, very important. I think it's very unfortunate. Biochemistry is filled with descriptions of things that I think lead students astray. So when we say a reaction is driven by the hydrolysis of ATP, we're not saying that ATP actually undergoes hydrolysis. What we're saying is that we've coupled that reaction to the endergonic reaction. Some species have canceled, and what you end up with is a net reaction. It's that net reaction that a particular enzyme is catalyzing. But we use the terminology driven by the hydrolysis of ATP. So neither one of these reactions is taking place. ATP is not being hydrolyzed. Please understand that. It's very, very important. I'm sorry that, you know, that it's turned out like this, that people speak so loosely. They should definitely speak a little bit more clearly, but please know that ATP is not being hydrolyzed. An alternate pathway is being provided. It's being driven by the energy available from ATP hydrolysis, this 30.5 kilojoules per mole. That's what's happening here. So let me go ahead and write that down. Write that down in red. Now, neither, actually, you know what? Let me do this on the next page here. Okay, next page. Okay, so neither reaction 1 nor reaction 2 is actually taking place. Okay. What takes place is glucose plus ATP going to glucose 6-phosphate plus ADP. That's the reaction that's taking place in the hexokinase. Let me go ahead and draw out what's actually happening here. So let me draw out my glucose here. I've got, you know what? Let me make this a little bit lower. It actually doesn't matter. That's okay. Boom, 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 boom. Let's go ahead and make this the beta form. This is OA, this is down, this is up, and this is down. Now we have CH2OH. This is our number 6 carbon over here. This is our number 6 carbon. So we have adenosine triphosphate. So let me go ahead and write this one over here. So we have O, P, O, P, O, P, O, ribose, and adenine. Boom, minus, boom, minus, boom, minus, and this is minus. So what's happening is the following. These electrons going that way, kicking up that way. This is glucose. This is adenosine triphosphate. What you end up with is glucose 6-phosphate, which looks, actually, do I have another page here? Yes, I do. Good. What I have now is this CH2. I have O. I have P. I have O. I have O. OH. 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 What I have is glucose 6-phosphate plus adenosine diphosphate, which is going to be O, P, O, P, O, ribose, and adenine, just so you can actually see what is happening here. This is ADP. This is the reaction that's taking place in the enzyme. The phosphorylation of glucose to glucose 6-phosphate is driven by the hydrolysis of HTP. It's driven by the energy that comes from the hydrolysis of HTP, but the reactions are coupled, species cancel, so the net reaction that takes place is this one right here. The glucose reacts directly with ATP to form glucose 6-phosphate and ADP. You'll see it written like this. Glucose 6-phosphate. ATP comes in, ADP goes out. This is the biochemical shorthand for it. This is how you'll see it. And hexokinase, they'll usually write the enzyme that catalyzes it there and anything else. In this particular case, there's going to be magnesium involved, the magnesium ion, but we'll get to that when we talk about glycolysis. But very, very important to remember, do not mistake what they say with what's going on. It's the net reaction that's taking place. That's the reaction that's being catalyzed by the enzyme. Okay, now let's go ahead and finish up here. Okay, let me see. Coupling. All right, so let's go ahead and do a quick recap before we leave our thermodynamics and spend more time talking about this idea of reaction coupling. So quick recap. We said that the delta G standard, there's a relationship between that and the equilibrium constant for a given reaction. That relationship is delta G is equal to minus RT ln KEQ. Okay, so delta G and KEQ are different ways of representing the potential for a reaction to want to go to equilibrium as written under standard conditions. Okay, we had delta G equals delta H minus T delta S. This expresses, it says that the free energy, yeah, I'll go ahead and just write it for this one. That's fine, that's fine. This says that the free energy is also related to two other thermodynamic properties, which is the enthalpy, the heat of the reaction, and the entropy, the degree of disorder of the reaction. Okay, so this, so if you want, you can set this equal to this, in case you need to derive a relationship between this and this, or this and this. So it's good. And of course, the final one, and the one that's probably most important, well, this one is definitely profoundly important. So the delta G of a given reaction under a given set of conditions, that could be any temperature, any concentrations for the reactants and products, that's equal to the standard, delta G standard, plus RT ln Q, where Q is the reaction quotient, equals C D over A and over B. I'll go ahead, you know what, that's fine. I'll go ahead and put these B and A. And this is at any given moment. So thermodynamics, this is pretty much what we're concerned with. Okay, thank you for joining us here at educator.com. We'll see you next time. Bye-bye.